And this brings us to the end of the first part of the lecture, where I just give you an additional task. And so this task is to be made at home. We will not make it in class, but you can just try it out yourself, discuss it with others. And if you need questions, you can always ask me that on the feedback session, which is organized next week. So the question is as follows. We have a human intervention, which is done on humans, and we are giving them the so-called Unimap tablet. It's a pill or a powder or a capsule, which contains all trace elements and all vitamins according to the recommended amount. So if you just take one of these tablets a day, you have enough intake for all your trace elements and all your vitamins. So we give this Unimap tablet, and in the tablet there is 30 milligrams of iron physically present. We have a second group, which is the control group, and that group receives a combination of iron and folic acid, whereby the iron has a level of 60 milligrams of iron in one tablet. So we want to compare the two groups, the control versus the intervention group. But if we look to iron, then we see that the control group has twice the amount of iron compared to the intervention group. And the question is, why is that? If we do in a human intervention study, everything should more or less be the same as much as possible between the intervention and the control. But in this case, there is a fundamental difference of 30 milligrams a day. Why is that? And also explain, if we have high intakes of iron or other trace elements, whether that could lead to potential risks in the human body, and try to explain which types of risks you might expect. And our next trace element that we need to discuss is iodine. Just the same as iron, I think the two major stories within the trace element chapter are iron and iodine. So you really have to understand what the element does in the human body. You have to understand more or less the mechanism of action, on where it actually interacts with different nutrients and organs in the body. And then finally, you also have to try to understand a little bit how we can solve the problems that we are facing with these two elements today. For iron, I explained the picture last time. So here you have a similar picture, which is now fully set on iodine. And what we measure is the median urinary iodine levels. So you can measure iodine status in the urine, which you cannot do with iron, but with iodine, this is possible because it's soluble in water. And you again, just the same as previously, you can find the status of different countries in the world as they were around 2005. So this is around 20 years ago, where you can see that we have the purple colors that are mostly linked to deficiency areas. And you can see already where the major deficiency areas are present. And if we go down the list, then you have an optimal phase, which not many countries are responding to. And then you have the darker gray zones, which are actually areas of toxicity. And you can actually see that in this situation, just let's say around 2005, that several areas in Latin America, as well as areas in Asia, and some areas, I think, but I have to check it carefully, but I think there are also some areas in Africa where we see that the levels are a little bit too high. Now, what is the reason for that? We generally knew that iodine was deficient in the past, that interventions were already taken, which was classically the use of iodized salt that could be used either in foods or either just as such added to the meal patterns. And usually these are governmental programs, so coordinated by the government. And you can see that in some countries where the iodine fortification started to work, that probably the process as such was not fully optimized, resulting in heterogeneous supply of iodine and potentially also forms of toxicity in the population. So in the meanwhile, we are 20 years further, The process is a little bit further standardized now. And the general, I would say, reference country where most people can refer to is Switzerland. It's a very small country here in Europe, so you cannot see it well on the map. But Switzerland, as you know, is a country that has several mountains. And iodine deficiency is especially prone in areas with high mountains, because there it is easy that the water-soluble iodine is flushed away from the soil and that it is not anymore physically present in the plants, neither in the animals that eat the plants. So generally speaking, for the people that are living in that society, you get a higher incidence of iodine deficiency. In Switzerland, everything is fully controlled. So it means that the population receives extra iodine in a very standardized control way. And there's also a very tight monitoring system to evaluate year by year the iodine status in the population. So in these conditions, the potential risk of having toxicities is quite low. While in the other countries where the fortification procedures were just starting up, there has been cases of toxicity and deficiency simultaneously. So it means that the supply is not optimized. The monitoring process, perhaps, with tracking down the status as a function of fortification, is not too well optimized yet, or the country is too big to do that. So in those situations, you do have some problems left. But year by year, we see that the system is getting more and more tightly controlled. In Belgium, we are mild deficient. Even still today, if I look to the more recent data of a couple of years ago, measured in the urine, then we still see that several people do not have an optimal iodine status. I wouldn't say that it is a very strong deficiency, but it's definitely not optimal. And it is important to know that because we have in Belgium still a quite important supply of energy by the use of nuclear power centers. We have one in the north, which is located not too far from Antwerp, which is in Doel. And we have them in the south for the French-speaking part, where also not far from the French border in Tihange, you also have nuclear power centers. In case there is a nuclear disaster, it is important to take in enough iodine because you need to saturate the thyroid gland to avoid that radioactive iodine can accumulate inside the thyroid gland. And this is the case for all countries that are more or less deficient in iodine. So for iodine, there's a little bit of a difference with iron, I would say. With iron, we don't know the exact solution. We have several options, but there is a difficulty also in measuring the status, in following it up, in finding the right technology or intervention that is needed to solve the problem. And as a result of that, if you look throughout time, iron deficiency in 2005 was there and was significant. It is still significant today in many countries around the world, including also Belgium. For iodine, the situation is different because, technically speaking, we know the solution. We're talking about iodized salt that needs to be supplied in the right content, the right amount, to avoid that we get deficiencies or toxicities. The problems that are still remaining with iodine are mainly at the governmental level, meaning that we need a tight control system, a good monitoring system, and we need to have a supply which is directly coordinated by the needs of the people. And there, especially in some countries who have very difficult monitoring systems or governmental structures which are not that tight, in those situations, there is still a need to further optimize the dissemination process. Here you have a more recent figure, but you can look at it in the notes, where you can also see that 20 years later, already many other countries are out of the iodine deficiency zone. But you still see some countries, the red zones, if you can see them, where there's still some risk at the moment for iodine deficiency. So what is the theory about iodine? We know that it is soluble in water. It can be transported in the blood as a free ion. It can actually go to the thyroid gland and it will be stored there for more than 99% of the iodine. So less than 1% of the iodine in the human body is not physically present in the thyroid gland. It can be oxidized, converted into diode, or it can be combined with proteins, which are called thyroglobulins, into the so-called hormones, which are the thyroid hormones like triiodothyronin and thyroxine, the T3 and the T4, because T3 contains 3 iodine atoms and T4 contains 4 iodine atoms. Those thyroid hormones are very important for normal growth and development. Think about the fetus, think about metabolic activity, heat production. Normal growth, like the length of persons, could partly also be linked to iodine. So there are many important metabolic aspects for iodine in humans. And the recommended intake is already known. It's around 150 to 200 micrograms per day. And if you're short of it, then you get goiter, which means a swelling at the level of the neck. So the thyroid gland will just become bigger. It mainly occurs in mountainous regions where the iodine is flushed away. It can also happen in regions where a lot of goitrogenic components are physically present in the food. Goitrogens are plant-based extracts, components that interfere in the iodine metabolism in such a way that it reduces the bioavailability of iodine in humans. And so you can get a deficiency of iodine even if you take in enough iodine by the food. In some countries, Belgium included, we also have iodine in milk. And this is mainly there because the iodine is an antibacterial substance. So it is used to, let's say, detoxify or neutralize milk containers after the transport of milk. And there are some remnants of iodine in the containers, meaning that the iodine can mix with the milk that comes in, and it gives you a natural source of iodine. It stays there, it's not toxic, it's useful. It is just intended to also increase iodine content by dairy product consumption. Here a picture that you can just look at. You don't have to know that by heart, but it just gives you an idea how the hormones are produced. So you start from tyrosine, which is an amino acid. It converts into the monoform, the D form. Then you have a condensation into the triiodoform and a condensation of the 2 diiodoforms into the thyroxine form, which is T4 and the other one is T3. These are the 2 iodine hormones. If we look a little bit into the thyroid gland, then we see that there are thyroid cells that have cytoplasm and where you still have some metabolism, and the follicles actually, which are responsible for the storage of iodine hormones. So the first thing that happens is that the iodine is transported by the blood. It is absorbed inside the thyroid cells. And there's a hormone responsible for that, the thyroid stimulating hormone, the TSH hormone, which is produced in the brains, transported in the blood, and responsible for the uptake of the iodides inside the thyroid cells. There they are oxidized with the production of iodine. You need oxidizing enzymes for that. And the iodine will complex together with the tyrosine amino acid, producing the mono and the D forms. And then by complex or coupling enzymes, you can go into the 3 form and the thyroxide form. And so the T3 and the T4 form. At numbers 1, 2, and 3 are the actual locations where goitrogenic substances will block the pathway. So if you take in simultaneously with iodine the goitrogenic substances, they will block the uptake, block the oxidation, and block the further transfer into the follicle where they can be transferred into the hormones. And so you need to remove these compounds by suitable processing to avoid that iodine becomes deficient. Now, if we look a little bit to the macroscopic effect, so the clinical effect, so you can see here what actually happens is a swelling of the neck. This is let's say, a limited swelling, but in some cases it can really become very big. And you get almost a football, which is just hanging at the level of the neck. But it is reversible. So if you give additional iodine, the swelling will be reduced and it goes back to the normal situation. On the right side, you can see the tablets, which are today available in all the pharmacists in Belgium, especially the pharmacists that are located within 20 kilometers outside a nuclear zone. It is important that these tablets are physically available to all consumers in case of nuclear disasters. And here on the bottom, you can see our former Minister of Public Health. It's already a couple of years ago because now we have already other ministers, but in those days it was Laurette Onkelings, who was actually a French-speaking minister who worked together with the bakery sector and who finally came to an agreement that all bakeries in Belgium would start using iodized salt in bread, so that we could more or less strategically increase the intake of iodine by the use of bread and bread products. And in Belgium, we are really a bread consuming country. If you could achieve that, automatically you will have a higher intake of iodine in the population. Now let's look at how this crop system is developed. And so how do you get to a goiter or an endemic crop? On the left side, you can see the normal situation. On the right side, you can see the deficiency of iodine. So in normal conditions, when iodine is there, then you can see that we have a hormone which is synthesized in the hypothalamus, which is the thyroid releasing factor. It can go to the pituitary gland, where it can synthesize thyroid stimulating hormone. It's a second hormone, the TSH hormone. This one is released in the blood, will go here to the thyroid gland, and there it will stimulate the uptake of iodine in the follicles. And so the iodine comes in, it's oxidized, and then it is taken up for hormone synthesis. The hormones can go to the rest of the body, or, and that is important, they can also have a feedback going back to the hypothalamus and blocking the release of iodine hormones, in this case, the thyroid releasing factor. So it means that the TRF and the TSH is blocked. They cannot go anymore to the thyroid gland, and the whole process stops. So there's no physical effects on the thyroid glands. And the normal follicles, as you can see them here on the bottom, have normal sizes. On the right side, you can see a disturbed situation whereby there is not enough iodine in the human body. In that case, you can see that initially we still have production of thyroid hormones, but as soon as the iodine amounts are lost or not sufficiently present, in that case, there's no release of hormones anymore. So it means that at number 5, there is no feedback anymore of T3 and T4 to the brains, and you will not stop the release of TRF and TSH by the hypothalamus. So you cannot release them, and it means that these compounds will continuously go to the thyroid gland, will continuously stimulate the thyroid gland to release T3 and T4, but since this is not possible, you see that the follicle is just blowing up. It's growing in size until it becomes a larger follicle, which can give you this endemic crop systems, this goiter, as we call it, which is an extension and enlargement of the thyroid gland at the level of the neck. And if you give iodine again, then the T3 and the T4 is synthesized again. The system restores, so you get a feedback. And in that case, there's no extra stimulation anymore of the thyroid gland, and the thyroid gland will slowly but surely go back to the natural status. So this is the story on iodine. I hope in this way you can have a good view on why it is important, what is the basic mechanism behind it, and what we can actually do in order to improve the situation. And then we come to the final element that I would like to discuss in this chapter, and this is selenium. So contrary to iron and iodine, which are two trace elements from which I'm pretty sure that there is a need for intervention, and where we could improve the current nutritional status, for selenium, it is less clear. But I would like to give it because I see that there are already a lot of initiatives which are taken in the industry to supply extra selenium to humans. So it is important that you know a little bit about it. Selenium is considered a toxic element in selenium-rich soils. So it could lead to so-called selenose, whereby animals as well as humans could take up too much selenium, which could lead to intracellular toxicity. The other way around also works, which is called selenium shortage. And this comes from a region in China, especially in the southern region, in the Tibetan region, where there was also a shortage of selenium, which was called the Keshan and the Keshan-Beck disease. Due to the fact that there's not enough selenium in the soil, so not enough selenium in the plants and the animals that eat the plants, and as such also not enough selenium in the humans that are living in that area. So both problems with undernutrition and overnutrition, and as a result of that, selenium was further evaluated. It seems to be absorbed in the organic form, and it can also be excreted by the urine. So it means that you can use the urine samples as a measure for the selenium status of selenium. We see that the function of selenium is mainly linked to antioxidant effects. I explained that when we were talking about the radicals and radical formation. And there's enzymes which are called glutathione peroxidase that can actually neutralize radicals in humans. And these ones are found in the cytoplasm as well as near the membrane. And as you will see on the next slide, depending on the status of selenium, the human body is very selective in synthesizing these types of enzymes either in the cytoplasm or in the membrane, depending on the amount of selenium that is there. There are many activities described for selenium. I'm not 100% sure that all of them are fully proven. It's still in a research phase. But let's say that for the antioxidant effects and the glutathione peroxidase activity, there are very clear indications that selenium status plays a role there. And here you can see a little bit the effects at the level of the DNA. So you can see that if we have a normal status, which is the left side, or if you have a deficiency status on the right side, then we see that in normal status, all the different enzymes that are linked to selenium are physically being produced. And this is done by using a selenium complex that interacts with the messenger RNA, and that leads to transcription and transcription. So you get a translation whereby the messenger RNA is translated into body proteins. The same for the other enzymes, for example, the ones that are located near the membranes compared to the ones that are located within the cytoplasm. All of them are synthesized so you get maximum protection within the cell. On the right side, the same presence of selenium, but in much lower doses, so you get a deficiency. In those situations, it seems that only the enzymes that are linked to the membranes are physically produced. So there's only interaction between the selenium complex and the messenger RNA that codes for the enzymes near the membranes, while the ones that are physically present in the cytoplasm do not get interaction and do not get any synthesis. So you see that the level of regulation is done at the level of messenger RNA, so the genetic material, and this one is determined by the selenium status of the human cell, which is actually called nutrigenomics, nutrients that can physically interact with genetic material to determine their own bioavailability and activity. And the final slide, which is here for this chapter, can show you more or less the situation of selenium content and status in Europe versus the USA. So on the left side, so this first Gaussian distribution, the light gray, is a situation in the UK, where they had an NDNS study, which was a survey that was done a couple of years ago, where you can see that the average mean value for selenium status is between 80 and 100 micrograms of selenium in the plasma. On the right side, you see the second distribution, which is the dark gray, and this is the situation in the US. So there's the NHANES study, which is also a survey that was done in that country, and where you see that the average levels of selenium in the blood is around 120 to 140, 150 micrograms per liter. So it is significantly higher than the average levels that we have in Europe. There's a reason for that. So in the US, systematically selenium can be added to foods so that the overall intake of the population in terms of selenium is higher than in Europe, where usually the selenium is not directly added to foods. So in that case, the status is a little bit lower. According to the current studies that we know about potential health effects, it seems that the optimal selenium concentration with minimum mortality lies in the area of 130 to 150 micrograms per liter, which is more or less the optimum that we have today in the USA. So if we take the two countries, because in Europe we don't have the fortification, in the US we have, it is very clear that if you start a supplementation campaign in both areas, the highest risk will occur in the US, because they have already a quite higher intake. If you would supply extra selenium by the diet, it means that the curvature will shift to the right, and it will give you a higher risk for increased selenium supplementation. In the case of the European situation, if we would start fortifying, well, not fortifying, but if we would give a supplement of selenium to humans, then they will probably shift to the right and will end up somewhere at the optimal concentration range. So the chances of risks are lower in this case for the European context than for the US context in case you're going to use extra supplements in the diet. So this will end normally the chapter, chapter number 6. I will stop sharing and recording here to listen to your questions